Yeah, cool. So today we are, you know, talking about MapReduce, right? And what is MapReduce? MapReduce is basically a distributed computing framework for Hadoop ecosystem. Is it just a distributed computing framework? No. Actually, it is a programming paradigm, right? It's a different programming paradigm. What do I mean by that? Okay, let's look into one, the first order of business, that is how traditional programs work, right? How traditional programs work. Traditional programs work in this manner, where your program and your data would be in one place, that is your disk, which is your hard drive or your SSD, right? These are stored. As soon as your machine boots up, both of them, either loaded to the data, or upon your request they will be loaded here. Okay, this is where your data plus program will be there. As soon as you run this program, right, this program would be transferred to the CPU as instructions. Okay, and these instructions will request the data from the RAM. If all of the data is not present in the RAM, it would go back to the like in a hard drive, and load that data into RAM first, and then process that again, load that into CPU and process it, right? This is all happening in one single place, in one single node, in one single machine. It could be your database, it could be your app server, like application server, or just some application, Java application or Node.js application running. It could be anything basically. So this is how a single node machine processes data. Okay, there is a centralized handling that happens. Okay, your application runs on the CPU, it is stored on your RAM, it is loaded from your disk, and as soon as you run the program, your CPU will take one instruction by one instruction. Let's say you have three instructions. One is read a file. Okay, read a file. Second one is filter records. Filter records. Okay, out of based on some condition. Third one is write the output file. Output to a file. Okay, these are my three instructions. Okay, these are my 1, 2, 3 instructions here. Okay, so what CPU this is my program basically. These are instructions. So CPU takes this. So read a file. Where should I read a file? Okay, I'll provide a path. Okay, filter records. What kind of records do you want to be filtered, or what kind of records do you want to end up? So I'll get that. So third one, where do I have to write a file? Okay, I'll give a path. So this is my program, or this is my set of instructions that I give to my CPU. Okay, based on that, it will load the data from this one. Okay, this is how all of the data processing happens on one CPU, and all of that happens in one machine. Okay, this is called centralized data handling basically. So suppose once you give instructions, right, what happens is CPU has threads. That means if you think about it, right, CPU is just an execution machine, like central processing unit. It just gets the instructions, it will execute it, and on the data, right, it will load the data, it will execute it, it will if you have to write it, it will write it. If you have to display it, right? So each CPU will have n threads. N threads meaning, like, you know if your program only needs one thread, like reading a file, filtering records, and it needs one thread, right? CPU will write only one thread. Okay, one thread. That means in rest of the n minus 1 threads, okay, there will be other operations going on, right? Like your this is your program. Okay, in other threads you can have music play going on, you can have your like a word document open. All of this happens along the way. So this is your single node machine. Okay, I'm just giving a normal like desktop scenario, not as on a server, desktop scenario, right? So if you're this program handles a lot of data, you could write multiple you could write a program to use n threads all at once, right? And then write process the data. Basically, this is called as multi-threaded execution. Okay, it is slightly more complex, but in terms of how you handle the resources on CPU and on your RAM and disk when everything is happening in parallel. But yeah, this can be done. So this is how you use to parallelize the process basically in one single node machine. Okay. So largely CPU based system, like single CPU based systems. So we learned this. Okay. And data plus programs. Okay, we have discussed this. Data plus program loads into RAM and CPU process it on the same machine. Okay. So we understood all of this. Any doubts here? Any doubts here? Nothing, right? Cool. So generally these instructions were written in some programming style called imperative program. Imperative program meaning basically you will give each and every instruction in a written format spelled out, and then the program, the CPU follows the program exactly like that. It doesn't change anything, right? Exactly like that. If you pass in bugs, it will run the bugs. If you pass in some issues with the logic, it will just do execute that step by step without making any changes to the program, right? If you write programs in Python, for example, or Java or C++ or C, right, you have to spell out how to read a file, how to filter records, how to write it to a play location. All of this should be spelled out. Okay. So this is how traditional programs work. There were, like declarative programming languages like SQL that runs on databases. These are like, like just you will give some instruction, right? Select star from table and it will do it, right? This also happens on a single node table, right? How it works under the hood is abstracted from us in a database, right? This is called as a declarative programming. Basically, you are declaring a statement here. This is a statement. How it is executed, the query engine in the databases will take forward, right? They will have their own query processing. I know how to plan, how to get the data. All of that will be taken care by this one. This is called as declarative programming. So this is how your traditional programs used to work. Okay, there is one more aspect to it, and we already talked about it. If you want like a lot of processing to happen, right, you can scale the system. This is called as vertical scaling, but it tapers off. The performance tapers off after some point, like 2x your resources will not be equal to 2x your performance, right? So that is what I have shown here. So the performance at this level and the performance is at this level has not changed. It is not equal to 2x, right? It is not equal to 2x, even though we have increased the resources basically, right? So that's what I'm talking. I hope you guys, caught everything. If you have any like doubts, please let me know. Cool. Right. Now, we have discussed Hadoop, right, in the last sessions on a lot of detail. And we understood that, okay, single node machines are not scalable for the data that we have. That's why we want to use a data distributed storage for, you know, reading and storing the data, basically. Now, what if we can leverage that system, the architecture of the system, to process the data at scale? Because the data is spread across, the nodes, right? Already. So, what if we can uh, process the data parallelly? So that's the need of the hour, right? Since we have already stored the data, we want in a distributed manner. We want to process that data in a distributed manner so that we would get like a lot of performance compared to what we already have on the traditional system or single node system, basically, where we will be we will face the bottleneck of system resources as our top ceiling, where we cannot store all the data in one single machine, right? So how do you do that? So the idea here is that single node machines, we know that, right? The processing, distributed data on a single machine is not feasible. What do I mean by that? Suppose you have a client, that is a very beefy machine, right? You want to get the data from single node. Like let's say my data is spread across three machines, right? Here one, two, and three. Suppose I want to process the data. If I write a program where it will read the data from this node first, this node later, and this node afterwards, and process data on read the data from here, process the data on the client, and then send back the data into a new location here, right, on each node separately, it would be a nightmare. Okay, my client could go down because of the volume of the data. Again, the network bandwidth on this particular machines is very constrained, right? So we cannot basically scale this model where the client reads the data, process it, and sends this one. So how should it happen? It should happen on the machine because we don't have to transfer the data, because network bandwidth is one of the precious commodities in this multi-node cluster setup. So we want to process the data on the machine, right? And we want to process the data at a time, at single time on all the machines at once, so that we would get efficiency. Because one person doing like work, right, for large chunk that takes 3 days. If I add three people here, I can break it down and do it in one day, right? So that's the funda, like basic principle. So that's the basic understanding, or that's the basic requirement for us. Okay, so how to process that data at scale? We have already seen that, right? Data is stored across multiple machines in blocks, right? In HDFS, the data is already broken up into chunks of 128 MB, and it is stored across multiple machines, right? This is our data chunks. Okay, this is our data chunks, and it is spread across multiple machines, by the way, right? We want to have a programming model that when I send a request, the name node or the master takes the request and sends the program to all the nodes here that has the data, because the name node has the block information where the blocks are stored, right? We already discussed that in the previous session. Since the name node has the block information on all the blocks, file block information on the name node, it can route that program to each and every node that it already has the data and run the tasks locally. Since we have client and this one, the data node and name node coordination going on, we can check the status of the job that is running on the machine parallelly at once, right? Any doubts here? Okay, cool. So let me take an example right here. We have a 500 MB file here, right? 500 MB file. That is 128 MB, 128 MB, and 128 MB. Sorry, right? 128 MB, and this is 116 MB, right? So this file is spread across four machines right now, right? This is block one, block two, block three, block four, right? So if I have to process this file and say, okay, these are my expenses from 10 years. So I have it in 500 MB file, right? And I want to calculate what is my latest and highest spend that I've ever made. So this is all the transactions that I have in a single file. So that is spread across all these nodes. So if I'm a client, connecting to my, I've stored the data in Hadoop cluster. So I don't want to get the data, single data block data 128 MB transferred to my client, my machine, or any server here, and then process it and send the data back here. That is a wasteful of resources like um, the CPU on this machine, the network bandwidth of the cluster, and even the processing power that we already have on the data nodes here, right? So that is why what we want to do is we want to process single blocks there, then and there. This is called data locality. That means wherever the data is, we want to store, we want to, wherever the data is stored on that machine, we want to run the programs and run in parallel. So how does that happen, right? So when we the whole point of MapReduce is MapReduce invented a model where I will send the program to master node. Master node will send the copies of the my program to each and every single node that has my data, because it has the metadata of all the blocks, right? Metadata of all the blocks of the file to all those nodes, and then it will process the data locally, and then one node will collect the data and store it in one place. Let's say that is D4. So that's the programming model. MapReduce does that. Traditionally, this was not the case. In traditional way, every instruction was done on a single machine at once, right? Here that is not the case. Here that is not the case. Okay. Now you can ask me like this 116 MB, this is a small file. The task completes very fast here. Yes, and these can be a little slow, and sometimes one of the nodes might go down, or the data might be corrupted. Yes, all of the coordination will happen within the MapReduce framework. That is guaranteed for us. A developer who wants to use MapReduce framework need not worry about the coordination between the nodes, the failures, the retries, the data corruption. All of the aspects is taken care by the Hadoop framework itself, be it for processing, be it for storage. Right? We already understood about storage. We will discuss about the retries, failures, all of that in the this session and as well as in the upcoming sessions. Right? So this is the guarantee that MapReduce program gives us, and we also want it. We also want these guarantees. Right? Suppose if we are running a distributed program, right, and it just fails on one node, and we don't have a mechanism to track that, so we would never trust that system, right? Like because it increases our load on our end, because we have to manually track that, the coordination, we have to like literally like hound behind the system and identify what's happening, whether the data is corrupted or whatnot, right? So that's not a good look. So MapReduce reduces that for us, right? MapReduce is helps us within that regard, right? So again, there is one more important aspect here. Suppose if my program is distributed across machines, right, every single time when my input data is same, on any machine, the output data should be same as well. Okay, let me tell you what do I mean by that. Suppose I have given a list of items here. Okay, I say that I want a maximum out of this, maximum number out of this, right? Every single time, if I don't change the input here, okay, which is this one, this list, the answer should be 5. Okay, this should be set in stone. If the input changes, the output changes as well. But my ask is I want to calculate this one, right? I want to calculate the maximum of a list, based on the input that I given, that was given. So every time if the input doesn't change, the output shouldn't change. Why? Because we have to determine the system how it works, right? If Somebody executed the same data on this block on this machine, the b2 block on this machine, and they got different result. Somebody has b2 block here because we have three replicas, right? And we got another result here, so gone. So that should not happen, right? So that is one major aspect here. That is one major aspect. This is called functional programming, by the way, and we will discuss about at length about this concept later on. Okay, right? We need distributed processing, and we need to be sure that okay, when we have an input, we should get the same output any given time in the future or in the past or present. Okay, any doubts on this? Cool. Right. Now, so we already know HDFS stores. So does it can it go for distributed processing as well? Yes, we will see about that. In the upcoming slides. What kind of programming model we could all of this? Yeah, this is basically what we were discussing. This one is basically MapReduce. I've just like jumped ahead and said that okay, MapReduce all of that. But any distributed framework, right? Any distributed processing framework, be it a data warehouse or a query engine that processes data, or even any distributed system, right? That should have these characteristics, more or less, right? So basically, what is map? What is reduce? What is deterministic function? What is war model? And what are the benefits of having raw layer and all of that? We will discuss now. So what is a map? What is a map? Anyone?
It stores key value pairs.
Key value pairs. Okay. 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 Got it. Yeah. Anyone else? Cool. Thanks, Uprit. Yeah. So a map is basically, saying that I have a list or set of values. Okay. I have a list of values and I have a function. Okay. Okay. I have a function. I have a list of values. Second, I have a function. So I want to apply this function on all of the values here. I want to apply this function to all of the values here. We will see an example about it, but yeah. So by the end of it, we will, suppose we have n inputs, right? N inputs. By the end of map, we will have n outputs, right? N outputs. So what do I mean by that? Suppose, let's say you have a table in SQL, right? You have a table in SQL, your DB, right? Your DB table, basically. Suppose you want to you have columns like first name and F name and last name, L name. So I want to create full name column, full name. So what happens here basically? Full name, right? Here we will do a string concatenation operation, right? That means we will like basically like add these two names and then we will create a new column called concat. So this string concat is a function. My table or my columns is list of values that I want to apply this string concat function to, right? So this could be represented as a map. Map is my function plus set of input values, which will give me n outputs for n input values. Okay, and this map, right, will always produce the same output as the same input, and it should always produce same output for the same input values. Okay, this is again functional programming aspect, by the way, that I know earlier mentioned. Okay, so that is what it is. An example here is your squared function. Okay, you are seeing, right? This is my input, that is 1, 2, 3, 4, 5, a list of values. I'll explain this here with this example. So I've just elaborated it a bit more. So I have list of numbers right here. That is 1, 2, 3, 4, 5. And in Python, the lambda is called as anonymous function because we don't have a name for a function, but it acts like a function. Basically, it is a function, but it doesn't have a name. So what it basically is doing is here it is querying the numbers. What numbers? The numbers that are present in this list called numbers, right? So lambda is basically an anonymous function or lambda functions in Python, right? This is basically Python syntax, by the way. This is all in Python. Okay. So I've just I'm trying to like establish a simple pattern of how map is applied, right? So here, if I have to elaborate this and write in a normal regular function way, right? I'll say, okay, def, that means define a function called square. It takes a input value n and returns a value of n into 2. That is square of that number. Sorry, n power 2. That is, n square basically, right? So here, same thing. This is a lambda function. It takes an input value of x and it calculates this value and returns it. Okay. On what values it does that? It does that on numbers. So this is basically your map. Okay. This map value, what we are doing is in Python, we are converting it into a list again. Okay. Map is a data type in Python, right? So this is what it is, right? So this is the function that is applied on the data, produces n output values for n input values. This is always map. Map is end-to-end mapping, basically end-to-end, n inputs and outputs. Okay. So what about reduce now? What about reduce now? Reduce is a function which takes n values and reduces it to one output value, right? So if you think about it, let's say I want to calculate, you know, a maximum number out of this list. Okay, max value out of this list. Max will always give one output, right? One output. Okay, like one single output. It doesn't give n values, one single value output. Okay, max function, min function, sum, average, all of these gives only one values out of any values that you input to that function, right? So numbers is this like list where we are again taking a lambda function here which takes two input values and checks for a condition. That is, if x, okay, I want to retrieve value x as the output. If x is greater than y, okay, else it is y, right? So if I have to elaborate this function again, this is a regular function. I have defined max function here, which takes in two input values. If x is greater than y, return x, else return y. This is how a normal function would be written. This function we want to apply again on a list called numbers. So here what will happen is we will get one output value for n input values. This is a reduce function. Okay, this is a reduce function. Always this map and reduce function are deterministic functions. Both of these are deterministic functions. Okay, that means any input value will, sorry, not any input value. For the same input value, we will get the same exact output value any given time in the past, in the present, or in the future, right? This is very important to understand because since we are doing this in a distributed manner, right, on different nodes, on different machines, we always know what we want the output as, and the machine should always give the same output for us with the same conditions, with the same input, with the same, we should get the same output all the time. We cannot compromise on that, right? So this is basically an reduce function. This is how reduce function works. Any doubts? Cool. So what is war model and benefits of raw layer? I'll explain it a little bit. Okay. After a couple of slides. So I guess everybody got this because this is really, 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 really important. Every single program or SQL, anything that you write in distributed systems works on these principles. Okay. Now, right. So we will come to this slide again. Right. So let me take a moment and just put all of the things that we have discussed now and make that into a single example, right? So we want to have a data processing happening in parallel, right, on multiple machines in a cluster based environment, right? Okay, suppose we have 4 node cluster here. Okay, this 4 node cluster basically has data stored in it, right? Let's say we will have 500 MB file here. Okay, we have 4 blocks. Okay, 4 blocks. Now, if you think about it, right? Why do we want a deterministic function here? Is that it would allow us to like do any sort of calculation, recalculate it, even after the job failures or node failures or app failures, any failure on the nodes, we can recalculate it and get the same result, right? And the one more important aspect is here the map function will never change the input functions in map or reduce, right? The map or reduce will never change the input of this function. They will always act on the input, but we for to get the output, right, we have to store it in a different variable. You are seeing that here your numbers is in one different list, your output is a different list altogether. You're not overriding any input data. Okay, these are all your functional programming aspects where you are passing your functions as an arguments, right, to the map function, and you are calculating or you are working with deterministic functions, and these functions will always produce the same output for the same input. These are functional programming aspects, and MapReduce uses them heavily when we are writing the file, when we are writing the programs. We will see that about the programs later, but yeah, right. So now once we understood that, let's take an example of a MapReduce working in a distributed environment with a normal nominal example of word count. So suppose my input have something like this string. Okay, quick brown fox jumps over the lazy dog. Okay, and there is a lot of text of 500 MB. What I will do is my block one will have this text. Okay, block two will have other part of the text. Three, four, all of these blocks will be in different blocks. So what this particular program does is the first order of business for any record in map is basically to convert your texts, right, into key value pairs, that is your maps. Okay, so what do I mean by that? Suppose I have a line here, okay, in my file, right? This every single new line will be converted to this one, line one and count one. We are counting words, right? Count. Let's say we have this document. Let's say the is present in 54 places or 54 times. Dog is present at 100 times, right? I'm just giving an example. This is what we want to do. This is what we want to do. This is your basically your word count program. Okay, your word count program. So before we do that, what MapReduce program does is when it is reading the input, any input for that matter, not just strings. Okay, your tabular data, your image data, your all of this, it will read in key value pairs. Basically, it will read in key value pairs. Okay, it will read in key value pairs. That means when we are writing it, it will just say that, okay, this is my input string, and this is my counter. Okay, since we are doing a map reduce one, it will attach a counter to it. This is my input string. Whether we want it or not, it's a different story altogether. We want it in this case, but sometimes we don't want it. Okay, each line will be converted into a key value pair. Okay, this happens on every single node, by the way. Every single node, by the way. Okay, right. Line 3, again, line 3, comma 1. Okay, line 3, comma 1. All right. So this is how it is done. Line 3, comma 1. So what we have to specify is here, this is, let's say, this is one line, right? All of this is one line, whatever you're seeing in the example, right? The quick brown fox jumps over the lazy dog. This is a very popular English, sentence which includes all the letters in the alphabet. So I've just taken this as an example, right? So all of this is single line, right? So here what happens is all this in the first stage when it is reading the data in the input one, this whole line, okay, this whole line or line one will be treated as single input file. So what I will do is I will break this single line or this sentence, basically this sentence, okay, into words. Okay, we will parse it into words. Okay, so based on the spaces that are present, we will, like remove, we will, say that, okay, this is one word, this is one word, this is second word, this is third word, like that, right? So we will convert that into this again, right? So this is basically your map phase. Okay, so this is basically your map phase, and this happens parallelly in your, data nodes of your Hadoop. So how does this work? How does this work? So what I will do is I will create, I'm a client here. Okay, what I will do is I'm a client. So in my machine, I will write a program, Java program basically. Okay, MapReduce is written in Java, a program where I will say that, okay, now read me the data in certain location on your Hadoop cluster. Okay, certain location like, like location one, and then there is text file called as word count text file. Okay, word count text file .txt file. Okay, in this location you have data. I'll write the program in Java, and it will say that, okay, for map phase, you need to read the data on this particular location into your, into your memory or on this machines parallelly in the map phase, and then, like parse these, text data into words and then count them, right? So in the map phase, I will write that. In the reduce, I'll say that, okay, whatever that is happening in the map, take that in to a reduce phase, and then basically crunch that, and give the final counts for each of the words, which is like this. Okay. So in the reduce phase, it will be the 54, the comma 54, dog comma 100, and so on and so forth. Right. So this is how it works in distributed manner. Okay. So when I write my code, I have to define my map phase, how the data should be, read, how it should be processed on single machine. When I want my final result, right, I will, define a reduce phase where I will get all of the data into one single place and then, dump it. So in the map phase, when we are, okay, understood. Any doubts in this one? Give me a second, guys. Right. Okay. So this is how we are defining, map phase, reduce phase, and all of that. We will see examples, code examples, all of that. Okay, in the next session, and we will see how again, edge cases, failures, all of that. In the next session, basically, we will see the program. We will see the cases, how failures happen, how we the execution happens, all of that, and we will see the logs of the execution, and we will see all the patterns there at once for the word count example. Hope you guys like this session. If you have any questions, we have a Discord group. I will upload this to YouTube and provide the Discord group over there, and we have to you can ask any questions over there, or in the video comments as well. Anything is fine with me, right? Yeah, I'm stopping the recording now.